So what we saw last time was two things: the definition of PRF security for a family of functions, and thus in particular a block cipher, as a new metric of security for these objects. We then saw an example of how we could assess whether a particular family of functions met this definition or not. And in our example, it didn't. We gave a simple attack that violated PRF security. And then what we came to is the question that, well, how well does AES or how DS fare as a pseudo-random function? And to give an answer to that, but also for many other reasons, we paused to discuss the birthday problem and how we can figure out the probability that two people in a room have the same birthday when birthdays are random days of the year, or more generally that we pick random numbers in a certain range. How likely is it that there is a collision, two of them being the same? And remember, the bottom line is it grows quadratically in the number of choices, inversely in the size of the set from which the numbers are drawn. So we're now going to put all this together by coming to some assessment about how well block ciphers fare as PRFs. So suppose you're given some block cipher. It could be AES, it could be DES. Let's say K is the key length, L is the block length. If it's AES, both have value 128, for example. I'm not telling you much more about the design. It is a block cipher, which means it obeys the mathematical definition of that object. But I'm asking you, well, go ahead and assess its PRF security. What does that mean? We can look at the games. We know that for any adversary A, there's an advantage that can be computed. Can you come up with an adversary that has a non-trivial advantage? It does something that manages to distinguish whether it's talking to E sub k or to a random function. So remember, this adversary has access to an oracle fn. It can give it an input x, which will be an L-bit string. In the real game, it gets back E under key k and x, where key k was chosen and initialized by the game at random but frozen and not given to the adversary. Remember, k stays static across all fn queries. There could be many such queries. In the random game, the adversary is just given back a random L-bit string as the response. We saw one example of a family of functions where you were able to give such an attack, and you're being asked the same thing. Look for some structure. What structure does a block cipher have that you might exploit and will somehow show you some kind of non-random behavior of the inputs, of the outputs for some inputs, even though you don't know what the key is. And we have two hints at this point. One is that the birthday problem has just been studied, so it's got to be relevant. The second is that I haven't actually told you much specific about E other than it is a block cipher. So the only thing you can exploit is the mathematical properties of a block cipher. And what is that property? That whenever you fix the key, the induced function is a permutation. That's about all you know. Okay, so with those hints, what can we notice? Well, here's what we can notice. We know that if you fix a key and then look at the outputs of E sub k for different inputs, because E sub k is a permutation, by definition, those outputs are all different, right? So suppose I'm talking to an fn oracle, which happens to be, in the real world, E sub k. I don't know what k is. Regardless of that, however, the outputs coming back from this box will be all different, assuming the inputs are all different, because otherwise you would violate the permutation property. However, if fn was a random function, no such restriction exists. The values coming back would all be random strings of length L, and so they could sometimes be the same. They might all be different, but maybe sometimes they won't, because random strings have some probability of sometimes being the same. Now, you might think that there is a difference there at a qualitative level, but it won't be terribly discernible. But that's where the birthday attack comes in. To see that, let's write the adversary. So as usual, we create a piece of pseudocode that plays the formal games we've defined, and this one plays the PRF game. That means it has access to an FN oracle. It needs to query that oracle on a few points and then return a bit with 1 to indicate I think I'm in the real world and 0 to indicate I think I'm in the random world. It picks some q distinct inputs for the family of functions. And q here is a parameter. You think of a different adversary effectively for every q. So we'll see that the advantage scales with q. Then for each chosen input, it goes and calls this procedure or oracle or black box on that input, and it gets back an answer y sub I. Of course, at this point, it doesn't know whether it's getting answers from the real game or the random game, and indeed its job is to figure that out. The metric it'll apply is it'll look to see if these answers are all different. If they're all different or distinct, then it says I'm betting I'm in the real world. And otherwise, I'm going to bet I'm in the random world. So in the first case, you return 1, otherwise you return 0. Now, clearly, if two of those things are not distinct, then this adversary actually is very sure that it's not in the real world. That simply cannot happen with a block cipher. So when it returns a 0, in that case, it could be very sure it got it right. But if they're all distinct, it seems more likely that it's looking at a block cipher, but maybe by chance it happened in the random world. Due to all this, we need to sort of carefully calculate an advantage. So let's do that slowly. How do you calculate the advantage? Once you have the adversary, you look separately at each game and you evaluate the probability that the adversary in that game returns 1. And then you subtract the two numbers. So I have my block cipher fixed, I have my adversary now fixed, and I start with the real game. In that game, the FN procedure takes the block cipher E, uses the key chosen here, which is unknown to the adversary, applies it to X and returns the answer. The same key will be used across all the different Q queries the adversary asks over here. It's going to now check here, this adversary, whether the replies are all distinct. How likely is that to happen? Well, we know exactly what these replies are. They are E sub k of the different X sub i's, and we know that E sub k is a permutation. So when you apply it to distinct points, these are distinct, you will for sure get back distinct outputs. So y's will always be distinct. So the probability that the adversary returns 1 is actually 1. It'll always happen. Okay, move to the random world. The block cipher hasn't changed. The adversary has not changed. It's the same piece of code. What's changed is the game it's playing, and the code for how FN works now on input X returns a random string of length this L over here. When the adversary returns 1, which is what we're interested in, is under the same condition as before. The replies coming back from FN have to be all distinct. So again, we assess, are they all distinct or not? Or with what probability does that happen? So what are these replies? Well, they're random L-bit strings. So the probability we're interested in is if I pick L-bit strings at random, Q of them, how likely are they to be all different? Okay, now that a priori may not be a very simple question. If we had never discussed the birthday problem, you might mull over that a little bit. But the observation to make now is that these are being drawn from a set whose size is 2 to the power L, right? There are 2 to the power L bit strings. The question of whether they're all distinct is the opposite of whether two of them are the same or that you have a collision. We know that the collision probability is denoted like this. So this probability is the probability of the complement event. So it's 1 minus the collision probability for throwing cue balls into 2 to the L bins. Okay. At the level that we make this assessment, we don't need to know what is the value of this. We've just pattern match the definition of the collision probability with this probability. Okay, but that's enough to get us a formula for the advantage. Block cipher fixed, adversary the same, its advantage for this block cipher under the PRF metric and this specific adversary is the difference of the two probabilities. We computed this as 1 minus the collision probability. Subtract them and you actually just get the collision probability. Okay, and now comes the time where, well, we'd like to actually get some sort of understandable numerical estimate. Actually, how big is this? A convenient way to do that is to use the facts we saw before to estimate the probability as roughly q squared divided by 2 to the L. Remember, it's this squared divided by this. We'll use a lower bound, so there's a 30% over here as per the fact. You can look it up on prior slides. The bottom line is that once q starts hitting 2 to the power half of L, this advantage is getting to be close to 1. Okay, close to 1, 30% for example is close enough to 1. If someone breaks your system or scheme with 30% probability or even 10%, it's an attack, right? So that's enough to be worried. So again, q has to be about the square root of this, which is 2 to the power L over 2. And so that's our conclusion. But this conclusion, which we alluded to before in discussing block ciphers, is really quite interesting and damaging or different from the point of view of how we see block ciphers. Because what it tells us is, for example, look at DES. Since the block size L is only 64, this attack succeeds in time 2 to the 32, and that's a pretty small time. So this DES is then viewed as quite insecure for under the birthday attack, and thus quite insecure as a PRF. It's not a good PRF. But we had already decided that DES is not good because it succumbed to key search attacks. And we had strengthened it. We had double DES and triple DES and all these things, and we decided that those were actually pretty good as far as key recovery goes. This one maybe less so because it's still a 2 to the 56 time attack, but this one a good deal more so. However, when it comes to the birthday attack and PRF security, they are no better than DES because the block size remains 64. So the same 2 to the 32 attack applies. And so this says that none of the DES family are going to be worthwhile if you want a PRF. For AES, this block size is 128. The birthday attack is still damaging. Its running time is 2 to the power 64, whereas the best key recovery attacks we know take time about 2 to the power 126 or something like that. So it's way better than exhaustive key search or even the best known key search, but still pragmatically it's kind of out of reach. And so even though it's borderline, we're willing to view this as being acceptable, and for practical purposes willing to view AES as being a secure PRF. Okay. And so that's kind of the takeaway we're going to go with. The takeaway is that we think of AES as a secure PRF and we think of DES as not a secure PRF. And at a high level, this is an illustration of how changing the metric has impacted our conclusion about the security of different block ciphers. Block ciphers that had looked fairly similar under key recovery security, say 3DES and AES, are now very different. One is secure, one is not. Also, as we kind of saw a little bit last time and we'll see more in the future, these are not merely theoretical weaknesses. This represents something that can be exploited to reveal information about encrypted data under 3DES, and that has led to 3DES being taken out of the list of approved standardized block ciphers. Okay, so metrics, as we've seen, can be more subtle and maybe interesting than one might have imagined. And also, as has been alluded to a few times, are really a central element in the understanding and study of cryptography. The extent to which we are better at our choice and of these metrics is going to influence security to a fair extent. And so we'll spend just a little bit more time for PRFs at least to understand security metrics. But we are far from done with that in the sense that in the context of other primitives, we'll keep coming back to this metrics question. So where are we? What's happened now is that we've seen that for one object, like a block cipher, we have at least 3 ways to measure security. 2 are very similar, 2 types of key recovery security, either consistent or target, both effectively saying, given input-output example and their hidden key, security means an adversary can't find the target key. We decided that's not a very good metric and gave this much seemingly different one, the PRF security, which is all the games we studied and intuitively says it's hard for the adversary to distinguish the input-output behavior of the block cipher under some fixed but hidden key from that of a random function. Okay, but we've also said in the past that key recovery security, even if it doesn't necessarily suffice for everything we want, is certainly desirable. There's no way we want a block cipher where it fails, where someone can easily recover keys. That would be devastating for security. Does that mean that we have to consider both these properties? But if so, well, how many other ones do we have to consider? The position taken in by cryptographers is that PRF security is kind of the global or master property, and it's the only thing we look at. And the reason for that is that all other properties, like for example KR security, are simply corollaries. In other words, I don't need to separately talk about key recovery security anymore, because if PRF security holds, automatically so does key recovery security. There's simply a theorem saying one implies the other. It goes further. Many other security attributes, many things from that list of security attributes we kind of saw in the beginning, are simply consequences of PRF security. And this is one of the reasons that this will be our metric of choice. Now, if I were doing the graduate course, I would actually show you that. I would give you a theorem and a proof that PRF security implies key recovery security. And we're not doing that here, but if you want a few words of intuition, the reason is that if I hand you a way to violate key recovery security, you could use that to violate PRF security, and you can figure out how to do something like that. In any case, going forward, what we want to remember is that we have AES, which we consider to be a good block cipher in the sense of PRF security. At some level, you might say that DES is also, in the sense that the only limitation is the birthday attack, and that's inherent. It's wound up and it's having a block size of 64. But for practical purposes, that attack is too doable to think of DES as having PRF security. And so if you're doing analyses or designs, you can exploit these assumptions. But you should also remember that they are merely assumptions. So I'm not aware of a better PRF attack on AES than the birthday one, but there's absolutely no proof something like this doesn't exist. You may find one tomorrow, someone else might. It wouldn't contradict any mathematicus that we know. Okay, so this is more exercises. So it just helps you develop familiarity and expertise playing with the definition of PRFs. It takes a problem which says that you are given a PRF which has k bits of input and output, and you want to double the output length. You want to create another PRF G which still has k bits of input but 2k bits of output. And it gives you various designs and it asks you, well, do you think they work or not? And so it may be fun to play with that.